Hello, I'm Mrs. Stevenson. Real and apparent weight. Your mass is 75 kilograms, and you are standing on a bathroom scale in an elevator. Starting from rest, the elevator accelerates upward at 2 meters per second squared for 2 seconds, and then continues at a constant speed. Is the scale reading during acceleration greater than, equal to, or less than the scale reading when the elevator is at rest? First, we want to decide what our coordinate system is. And for this problem, we're going to make the upward direction positive and the downward direction negative. If we take a look at our motion diagram, we see that the velocity starts out smaller than it ends up. So the acceleration is in the upward direction. Now, in order for there to be an acceleration, there has to be an unbalanced force, and that is our net force. If you compare our force of the scale, which is in the upward direction, and the force due to gravity, or the weight, in the downward direction, this is where our net force comes from. If we took this component of our force right here, and we drew it the same size compared to the force of the scale, this remaining force is our net force. And you can see that the arrows are about the same size and they're in the same direction. And now this problem has two parts of the motion of the elevator. There's a part where the elevator is going at a constant speed, and there is a part where the elevator is accelerating. And we are just going to look at the part where the elevator is accelerating. So we're going to list our knowns and our unknowns. In this problem, our known, we're given the mass of the person, or your mass, which is 75 kilograms. We are given the acceleration of the elevator, which is 2 meters per second squared. We're given the time that the elevator accelerates, which is 2 seconds. We also know the acceleration due to gravity is 9.8 meters per second squared. Our unknown is what we are solving for in the problem, and that's the force of the scale while the elevator is accelerating. For this situation, we're going to go back to one of Newton's laws, in that the net force on an object is equal to the object's mass times its acceleration. Put our 0 here. So the net force is equal to the mass times acceleration, although we talked about with our force arrows that the net force is also equal to the force of the scale, which is up, and the force due to gravity, or the weight. Now remember, because this is in the opposite direction, we have to give it a negative sign. That negative sign simply means it's in the opposite direction. And since this problem asks us to figure out the force from the scale, we want to get that by itself in this equation. So when we rearrange this equation, we're first going to add the force due to gravity, or the weight, to the other side, and find that the force from the scale is equal to the net force plus the weight, or the force due to gravity. So we're going to use this when we do our final calculation. When we look at the elevator at rest, meaning that it's not accelerating yet, we can actually figure out what the scale read ahead of time before it started moving. We're going to use the same thing. The F scale, or the force from the scale, is equal to the net force, but in this case, because the elevator is not accelerating, there is not that net force going in the upward direction, so that net force is going to be 0 newtons. And our force due to gravity, or weight, you will always calculate that by taking the object's mass and multiplying that by the acceleration due to gravity. So when we go to figure this out, we're going to take your mass, which was 75 kilograms, and multiply it by g, which is the acceleration due to gravity, 9.80 meters per second squared. When you multiply this through, you find that the weight of the person was 735 newtons. So we're going to take this f of g, plug it back into our formula for our scale for the elevator at rest. So we're going to plug in our 735 newtons. When you add that to 0 newtons, you find that the force of the scale in the upward direction, which remember was positive, will be 735 newtons. We're going to scroll down here to give us a little bit more room because the problem asked us to compare the elevator at rest to when it was accelerating. So now we have to look at the situation when the elevator is accelerating. We still have our same formula. The force from the scale is equal to the net force plus the weight, or the force from gravity, except in this case our net force isn't 0 anymore because we are actually accelerating. And from before, remember that according to Newton's second law, a net force is equal to a mass times its acceleration. And then for the weight, we plugged in the object's mass times the acceleration due to gravity. So our force of the scale is going to equal mass times acceleration plus the mass times the acceleration due to gravity. Both of these terms have m's in them, or mass, so I'm going to factor that out. And all we have left is the acceleration of the elevator plus the acceleration due to gravity. I can plug in my known values from the beginning of the problem, and the mass of the person was 75 kilograms. The acceleration here is the acceleration of the elevator, which was 2 meters per second squared. And then we're going to add g, which is always 9.80 meters per second squared. When you add together 2 and 9.80 and then multiply by 75 kilograms, you get a force of 885 newtons, and this is the force of our scale in the upward direction. When we compare this force, 885 newtons, to our force from the scale at rest, when the elevator is at rest, that was 735 newtons. So you can see that the scale reading when the elevator is accelerating is larger than the scale reading when the elevator is at rest.